All right. So, welcome back. All right, so Ting and I spoke about the exam, and what we decided was that we were going to hand out the exam on Wednesday and give you 24 hours to turn it back into us. And so you're going to need to be able to print your exam and fill it out and take it again, or take it and turn it in. And so I want to make sure that there's no major challenge there for people. If you foresee a challenge printing out the exam in that time frame, would you please raise your hand?
Would we be able to annotate it like on a tablet instead of printing it out?
It's fine with me if you want to do it that way.
Okay.
So 24 hours is enough time. No one has a logistical challenge with generating a copy of the exam or anything like that. Okay. So it will appear in your inbox on Wednesday, and you'll have 24 hours to return it to us. The exam is a closed note exam. You should use no resources. We will give you what you need, character tables and stuff like that, okay? And you need to know the periodic table. You will not be given a periodic table. The first question on the exam is fill out the periodic table. And you don't have to do the lanthanides and the actinides, but you do have to do all of the alkali metals, earth metals, transition metals, main group, noble gases. So if you don't know the periodic table, you're going to be in trouble because you're going to be asked to do some periodic trends and estimate the different, sizes and acidities and stuff like that of the various elements within a period or a row. So if you don't know where those elements are, you can't answer those questions. So you have 2 weeks to learn the periodic table now, and you'll get it figured out, I'm sure. The second half of the class, you're really going to need to know the transition metals because you're going to be asked to do electron counting. And if you don't know that off the top of your head, it's going to be hard to participate. Rachel?
Should this be like we can spell Roentgenium, or is it like the symbol for it?
Symbol is fine. You don't have to be able to spell terbium. Just the symbol. Of course, it helps if you know what element the symbol refers to. So that's assumed, but okay. And so then basically the rest of the exam is going to be problems that you've kind of seen already. You're going to have to do Lewis structures and Vesper and resonance structures. You're going to have to do symmetry problems. And, I put up some notes that I took from a meeting I had last night with one of your classmates explaining how to recognize symmetry groups. They are on Piazza, if you want to take a look at them. They're not complete, but it's a pretty good collection of the major symmetry groups there, which you can classify by their shape. I don't need to do the flow chart like you see in the book. The flow chart is for beginners. You need to learn to be able to do symmetry group assignments without that flow chart, just by looking at the shape. And you'll get better at that with time. So there's notes on how to do that on Piazza. You're going to have to do a substantial molecular orbital diagram problem. And it will be one you haven't done before. And it will be, it will make you reach a little bit, I think, but it's accessible. So you know, the homework problem we did for water and the problems we'll do in the notes in lecture are your only practice for that. And you know, you really got to be able to do this generation of a reducible representation for the ligands and decomposing it into the component irreducible representations. That's kind of the hardest part for you guys at this point. And then you have to be able to write the lines on a piece of paper and order them in energy appropriately. You need to know the ionization energies of the orbitals that you're going to use. I won't be giving you those. So, you know, and then you got to be able to connect the dots. And then also you have to be able to draw salcs. The salcs are these orbital drawings where you show how the atoms around the central atom combine, and label them with the Mulliken symbol and that kind of thing. And that's about it. So, you know, it's very similar to the exercises you've already been given, but you have to be able to do them in that 24-hour period. So, you know, no collaboration is allowed, no using materials outside of the exam. And I hope that, you know, that experience of really being on your own there will show you what you know and don't know, and you'll learn from that. This is, in my mind, the hardest part of the class is kind of like getting over this hump, and things will be downhill from here. It doesn't mean it's easy, but it, you know, there's less like, you know, less of a meat grinder going forward. So buckle in and try hard to get this interim stuff figured out, and then you'll be feeling good on the other side. Okay, so remember 2 lectures ago, we talked about pi donors and pi acceptors, and how if you have an electron and you bring up another electron pair, the energy of that combination goes up for the antibonding orbital. It goes down for the bonding orbital. But if you look at the ionization energy of the thing as a whole and you forget about the bonding and antibonding and just force 2 electron pairs on top of each other, it becomes easier to pull an electron out of that situation. That means higher in energy, closer to vacuum. And if you have an acceptor orbital and an electron pair, and you associate those, the acceptor orbital provides a place for the electron pair to become more stable. It is a source of positive charge, that acceptor orbital, that stabilizes the electron and makes it harder to pull an electron out. That is acid-base theory and redox and how they interact. This 2 electron pairs on top of each other is increasing basicity, right? You're putting 2 bases on top of each other. And that situation, that higher density of negative charge, makes it easier to ionize it. That means the energy of that collection of electrons is closer to vacuum. Positive charge plus electrons together drops the energy of the electrons. So you got to have that concept in your mind when looking at these diagrams, and you have to be able to apply that idea to move the levels around appropriately. So, you know, use that to check your diagram and make sure your diagram makes sense. So last time we went through and we did 6 ligand sigma for octahedral, and we decomposed it into its components. And we decomposed it using the formula, if you want, or the way I like to do it is by saying, I know that there are orbitals on that metal center in the middle of that octahedron that are going to overlap with the ligands. And so the metal orbitals are probably going to have the same symmetry as the ligands. And the character table tells you what the metal orbital symmetry is. It tells you X, Y, Z, those are the p orbitals. It tells you x squared minus y squared, z squared, xy, xz, those are the d orbitals. And I know that dz squared and dx squared minus y squared are the ones that point toward the ligands on the axes, because I always orient my axis system along the z, right? My z is the principal axis in my molecule, it's sort of the vertical axis, usually in the orientation that I draw. And so in an octahedral complex, that means that dz squared points at the ligands and x squared minus y squared points at the ligands. And the other three, which all look the same, xz, yz, xy, those point in between the ligands. Now, because I know that, I can look at the character table and say, ah, z squared and x squared minus y squared are the ones that point at the ligands, and they are EG in octahedral. So probably there's a ligand combination that matches them. So my 6 ligand sigma is going to have an EG in it. And it's going to have the p orbital one in it also. The p orbital combination of ligands is T1U, because px and py and pz are T1U. And an s orbital is spherically symmetric, and no matter how you translate it and reflect it and whatever, that s orbital, which sits in the middle of the coordinate system, is a 1 in all operations, and that's A1G in octahedral. So there's this totally symmetric combination, there's the p orbital like symmetry, and there's the d orbital like symmetry. So I know how to decompose my 6 ligand sigma. I can even build my 6 ligand sigma by knowing that there are orbitals on the metal that overlap with those. Now, sometimes there are other contributions, and we'll see that in the pi symmetry lone pairs that we're going to do today. But knowing that, having that intuition about the fact that the metal center's orbitals overlap with the ligands, and you can look them up in the table, will give you a good starting point for decomposing the reducible representation into irreducibles. Okay? All right, so, and then we drew the cells. And then we drew the orbital splitting diagram, and we saw EG and T2G on there, and we said, hey, that's the frontier orbital basis set. And those frontier orbitals are where the action happens. That's where you see the colors of many transition metal compounds coming from that have D to D transitions. So we started talking about that splitting. See if I can. There we go. We started talking about that splitting. We gave some examples, and we said, you know, as you go down a group, you go from cobalt to rhodium to iridium, the bonding increases in strength, and this splits the EG and T2G further, because EG in that frontier orbital basis in octahedral is sigma star. And so when the bond strength goes up, sigma star goes up. So cobalt's bonds are weaker, sigma star is here. Rhodium bonds are stronger, sigma star is here. Iridium's even stronger, sigma star is there. And so that spacing and energy goes up as you go from cobalt to rhodium to iridium. We also looked at cobalt hexacyanide, which is 3- instead of 3+, and we found that the splitting was larger. And said, well, there's a lot going on there. There's the sigma donating power of a cyanide, which is a pretty good donor. There's the pi accepting character of the cyanide, which is pretty good too. And then there's the charge, and all of those things kind of work together. So let's take a look at another set today. We're going to do chromium 3. So this is a D3 metal ion, and it has a 1 T2G 3 2 EG 0 electronic configuration. So let's take a look at a couple of examples of these sorts of complexes. So chromium hexachloride 3-. So when I do the math on this thing, this is also a D3 ion. We got 6 chlorides around that. Complex is 3- overall. So it's really like chromium trichloride with 3 chloride minuses stuck. And the delta octahedral for this compound is 13,200. Let's take a look at chromium trichloride hexafluoride. 15,200. Splitting is larger there. Now these halides are pi donors, right? Let's do some chromium hexaqual. In another world, we would have samples of these for you to look at. To see all the wonderful colors. Down here, these are sigma donor only. Water is not much of a pi donor. It's really kind of just a wimpy sigma donor. Ammonia is really only a sigma donor. It doesn't do any pi donation or accepting. And so now the delta O is larger. So why is the delta O larger down here? We went from 3- to 3+, right? So in a positively charged complex, the metal center is going to pull the ligands in more tightly to it. And that's one reason the splitting is larger, right? As the charge goes up, the splitting will go up. The metal ion pulls the ligands in more tightly, you get better overlap, the splittings go up. The other thing that's going on is that the complexes on the top are actually have pi donor interactions. So the halides, these lone pairs in those halides can do pi interactions, and that also impacts the delta O. And it makes it smaller. So we're going to do the math on that. Let's see here. Cobalt hexacyanide 3-, which maybe you can see in your notes, is 33,500 wave numbers. That's the last one we did in class. That one has an even larger splitting. So there you have stronger donation, you have a negative charge, like the ones with the small splitting on top, but the total splitting is greatest, 33,000 wave numbers. So that delta O is the largest, even though it's 3-. If you want to describe all of these trends, you need to account for pi effects. You can't just consider the charge on the molecule. You have to consider the local bonding, the donating power of the ligand, and in a sigma and in a pi sense. All right, so we need to understand pi bonding. And pi bonding, you know, these are small impacts, excuse me, on the total, but they are required to understand the color. So let's take a look at cobalt, hexafluoride. Now, each fluorine on the cobalt has 2 pi symmetry orbitals. Oopsie. That worked out. Okay, so there's a, call this one PZ, and call this one PX. Or you could say vertical and horizontal. So when you have an octahedral complex, you actually have a whole bunch of these little guys. You can think about each vector here as a p orbital, right? So p orbital is plus in this direction and minus in that direction. So you can kind of think about it as like a little XYZ coordinate system on each fluorine. We can represent the X and Y and Z directions with those little individual vectors. So in order to decide what the symmetry looks like for all of those lone pairs, to add them to our molecular orbital diagram, we can then take this vector we've drawn here and apply the symmetry operations to cobalt hexafluoride and try and decide, you know, what they're, whether they move or not, whether they're inverted or not. Now, when you do planes, you have to invert the sign of the wave function and you can get a -1 instead of just a 1 or a 0. But, you know, try to do that process on all these little vectors for that cobalt hexafluoride, if doing it by inspection is basically impossible. I mean, you could, but I think you would use a lot of paper and sweat. So that's not the way, okay? So one of the clever ways to figure this particular one out is just to multiply an XYZ coordinate system times the 6 ligand sigma. So you sort of generate a reducible representation that is a little XYZ coordinate system at each cobalt, okay? So an octahedral if you take gamma 6 ligand sigma and multiply it by gamma XYZ, you can get gamma 6 ligand sigma plus gamma 12 ligand pi. So each one of the fluorine atoms of our cobalt hexafluoride, one of the vectors points at the cobalt. That's going to either be X or Y or Z, depending upon which fluorine it is. The other 2 vectors, which are the lone pairs, will be the other part of the XYZ coordinate system. So when you multiply 6 ligand sigma by XYZ, you'll end up with the sum of 6 ligand sigma and 12 ligand pi. So we have an E8C3, 6C2, 6C4, 3C2, I, 6S4, 8S6, 3 sigma H, and 6 sigma D. And this is 6, 0, 0, 2, 2, 0, 0, 0, 4, 2. And how do you know what XYZ is? We did 6 ligand sigma by inspection last time. How do we know what XYZ is? Where do you get gamma XYZ from?
It's the S orbital, correct? It's the S orbital.
XYZ is a coordinate system. It's a vector from the starting at the origin, pointing along the X, Y, and Z directions. It's not an S orbital. How do we get that?
Well, you can do it like with the vectors and do it, you know, go all the way across and do all of the symmetry operations, or you can get it from like a character table to see where the molecule symbols that correspond to them are, and then input them into here, right?
Yeah, so that's right. So let's just say that a little bit more explicitly. So that's exactly right. You could do it by inspection, and you know that takes some time. You can very easily just go look it up, right? How do you look it up? Well, XYZ coordinate system is one of the three, you know, that's the linear functions, right? Linear functions, they're provided for you to you on the character table in the back. Sometimes they transform together. In octahedral, XYZ transform together. And so it's going to be T1U. Okay, but in other cases, there'll be X over here and Z over there and Y over there, or Z here and X and Y there. So those linear functions will be associated with a particular irreducible representation. It's on the table. You just go look. And S orbital is on the table too. That's the one where you have ones in every category, because any operation you do to an S orbital just returns the S orbital back if the S orbital is at the center of the molecule. Okay, so those things, you can just go look them up on the table. Gamma XYZ is there, it's T1U. That's a 3, a 0, a -1, a 1, a -1, a -3, -1, a 0, a 1, and a 1. Okay, got to know that XYZ is in the table. The d orbitals are all listed in those character tables. So if you want to know those irreducibles, you can go get them. All right, so now you do the product of these two. 0, 2, -2, 0, 0, 0, 4, and 2. And now you subtract the 6 ligand sigma from here to get 12 ligand pi. And we have 12, 0, 0, 0, -4, 0, 0, 0, 0, 0. Okay. So The gamma total, this thing here we're going to call gamma total. The gamma total is A1G plus EG plus T2G plus T1G plus 2T1U plus T2U. And figuring that out by inspection is a pain, but it can be done. You could use the formula. Or we can take our 6 ligand sigma, subtract it from the gamma total to get the 12 ligand pi, and we know gamma 6 ligand sigma is equal to A1G plus EG plus T1U. 12 ligand pi is therefore T2G plus T1G plus T1U plus T2U. Okay, so we pull out the 6 ligand sigma from the gamma total to get the 12 ligand pi. Now, what are all these? What is all this gobbledygook here? Do you recognize any of those symbols? In octahedral? T2G and EG are the d orbitals in a metal complex that has octahedral symmetry, right? EG and T2G. So there's a T2G. So this is going to have some bonding interactions with 3DXY, 3DXZ, and 3DYZ. This is a collection of pi symmetry p orbitals that overlap with the DXY, DXZ, and DYZ. T1U is another one, right? What's T1U? Has the same symmetry as 4px, 4py, and 4pz. T1U is the 4p symmetry. So there's some combination of lone pairs on the fluorines that overlaps with the 4p orbitals on the metal. T1G and T2U, they don't have any partners. There's nothing on the metal that has T1G or T2U symmetry. So these linear combinations of lone pairs don't overlap. So if you have 2 pi symmetry lone pairs for every fluorine, and you've got 6 fluorines, you get 12 lone pairs. But if you made a formal double bond using those lone pairs, the most you could make is 6. It's not the right symmetry to make more than that. Throw in some f orbitals and things change. All right, so many of the 12 pi symmetry orbitals do not have the correct symmetry to make bonds with the metal center. So let's draw some of these guys out. So we're going to draw some bonding cells. So T1U. So what is this thing going to look like? What's a T1U MO going to look like? Anybody know?
It's a 4p orbital, right? That's how we had it from the last class, where the metal has, it's a p orbital, 4p orbital.
That's right. It's a p orbital on the metal. And the MO must also have that symmetry, right? The component orbital on the metal, it has the same symmetry as the things we're combining with it. So if we just say, all right, let's draw some p orbital here. That tells you the symmetry of the wave function. Now, what combinations of ligand orbitals will also give you that symmetry? They're the ones that make a pi bond with it. That's T1U. Let's do a T2G. What's T2G? What's T2G? What is it going to look like? In octahedral, T2G is which kind of orbital? On
D
the metal.
orbitals,
D orbitals, which one?
X, Z, Y, Z, and X, Y.
Those are the ones that point between the ligands. Okay, so there's some ligands. Let's draw a d orbital in there between them. Let's shade our d orbital appropriately. And let's add some fluorine p orbitals that make pi bonds. We're drawing the bonding combinations here. There's a T2G. All right, these things are triply degenerate. Right? You just change the direction along which you want to orient the thing. And this p orbital, remember here, this guy combines, sorry, the MOs combine sigma character with pi character. Because remember that 4p orbital on cobalt also makes sigma bonds. That piece of the MO is not represented here, but you could just draw a sigma orbital above and below the p orbital and it would have the same symmetry. So there's a sigma combination that's T1U and a pi combination that's T1U, and the MOs are linear combinations of all. The d orbital here, however, is non-bonding in a sigma only sense. And so it's pure pi. Okay, let's do the non-bonding ones. T2U looks like this. You got vertically oriented p orbitals that have inversion symmetry. Sorry, are Ungurata with respect to inversion. That orbital is Ungurata with respect to inversion. And there are 3 of them, pick the direction with the 2 dots. The 2 dots imply no contribution up there. You can pick those along X, Y, or Z. There's no orbital that overlaps with that combination of ligand orbitals. T1G better be Garada. No, let's do it. No, got that wrong. I got that wrong. Darn it. Did it twice. I got this one backwards. That's why. There we are. Again, there's no orbital on the metal that combines with that collection of p orbitals. You can see how the phase of this thing kind of has like a rotational quality to it. Plus minus alternating as you go around the ring. Okay, so this type of thing, these MOs that we just did, they apply to carbon monoxide, cyanide, phosphorus trifluoride, halides, all of them. The sort of components that you're adding together to make up the MOs are the same. You just got a pi symmetry orbital and a metal-based orbital, and they combine. And if there's 2 pi symmetry orbitals on each atom, that's of a ligand, like carbon monoxide and chloride both have 2 pi symmetry orbitals, then this result is a general result you can apply to any compound. But some things are a little bit trickier than this because you don't have 2 pi symmetry orbitals on each ligand. Okay, so then you can't do this 6 ligand sigma times gamma XYZ to get the gamma total and then break it apart into 6 ligand sigma and 12 ligand pi. So this works nicely when you have, an XYZ coordinate system on each atom of the ligand, but it doesn't if it's not like that. So some fragments only have 1 lone pair, NR2, for example. All right, so let's do the MO diagram showing this stuff. And we're going to do the sigma only picture and the sigma plus pi picture like we've done in the past. And we're going to combine a metal with 6 ligand sigma over here and 6 ligand sigma plus 12 ligand pi over here. So we're sort of already used to this. We've got our 6 ligand orbitals here. And we have our 1, 2, 3, 4, 5 metal orbitals here. And we know that we end up with a 1, 2, 3 non-bonding T2G set and 1, 2 sigma star EG set, and then a bunch of bonding orbitals. Now, when we do 6 ligand sigma plus 12 ligand pi, we've got 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And the 6 ligand sigma is A1G, EG, T1U. The 12 ligand pi is T1U T2G T1G and T2U. And we know that the T1G and T2U guys are non-bonding. So let's pull those out. 1, 2, 3, 4. Sorry, let's not do it that way. Let's do it 1, 2, 3, 1, 2, 3. We've got T2U and T1G non-bonding. And then we're going to do 6 ligand sigma down here. And then we're going to do 2 different pi symmetry interactions. Where this one is T1U and this is T2G. Now, why did I do that? T1U and T2G are different than each other. Remember, T1U is a pi bond with 4p. T2G is a pi bond with d orbitals. Which pi bond is better? Stronger. D orbitals are, because they're closer in energy than the p orbitals. The 4p orbitals don't really do a great job of bonding with anything. So their perturbation on the ligand orbitals is small, and so the splitting is small. The T2G splitting is larger because the orbitals are closer in energy, their overlap is better. So the T2G comes down further to make pi bonding. Now, EG sigma star is here. T2G pi star is there. The delta O for the sigma only case is larger than the sigma plus pi case. It happens this way because these guys here, you can think about them as the d orbitals. And if I had an electron on my metal and a ligand lone pair on my fluorine, and I bring them up to each other, the d orbital is going to go up with the metal. The electrons are going to increase in energy as you push them together. And so it goes up, right? This makes the delta O smaller. Delta O gets smaller when you have pi donor ligands. Let's do this again. This time, we're going to do pi acceptors. So we've got our metal and our carbon monoxide. And we're going to take our 1, 2, 3, 4, 5 d orbitals here. EG and T2G. And we're going to take our 1, 2, 3, 4, 5, 6 ligand sigma here, which is A1G, T1U, EG. And we're going to take our 12 ligand pi one too many up here. Now I pulled a fast one on you because I put the pi star orbitals of the carbon monoxide above the metal. Yeah, this is a CO pi star we're interested in. Is above the metal. Not the case when you're talking about the cobalt one, right? The cobalt one, all the ligands started off down here compared to the metal. And now we took out this 12 and we put it up here to get to this diagram. You have to be careful about the ordering when you do this. So we're going to have some 6 ligand sigma. I guess I'll just say sigma. I'll just ignore those and not pay too much attention. And then I'm going to get those sigma stars up here. A whole lot better. And now we're going to make our pi bonds with T2G. We're still going to have 1, 2, 3, 4, 5, 6 non-bonding orbitals, right? It's T1G and T2U. And then we're going to have our T1U and our T2U. T2G. Okay. So note here, we've got pi bonding in this case and pi star. So the orbital parentage for the bonding combination looks like the d orbitals. The antibonding combination looks like the pi stars. Okay, so by starting this 12 ligand pi above the transition metal, now the d orbitals here go down in energy. And that delta O gets larger instead of getting smaller. Okay. So remember, pi star higher than the metal, and then it'll turn out right. Okay, so in summary, comparing pi donors, sigma only, pi acceptors, we're going to have EG and T2G, where both of these guys, we got a sigma star here, and we have a pi star here. Sigma only, sigma star, non-bonding. Oops. Pi acceptors, we have sigma star, and we have pi. And so the delta O's here reflect that. Pi effects impact color when you have D to D transitions. So there's a bunch of different ligands, and their impact on delta O is well known now. Delta O decreases this way. Okay, so the spectrochemical series reflects this ligand field situation. Strong pi acceptors really give rise to large ligand fields, colors that are, you know, more like yellow. Well, the splitting is large, so it absorbs UV light, right, or blue light. But that means is a yellow color that you see. That's the color you would collect by eye. These things with really small splittings, when you got pi donor ligands, they're going to be blues and greens and purples. Sigma only will be intermediates, roughly speaking. You know, it depends upon the metal ion, depends upon the charge state of the complex overall, but those are the basic trends. All right, so the magnitude of the splitting also has a really big impact on other properties like the spin state, which we're going to talk about. Just a few periodic trends here. For MLN complexes that span -4 and +4, some things that we need to be aware of. Oxidation states for transition metals go. Go up as you go. Okay, so when you start on the left and you start heading over towards chromium, molybdenum, and tungsten, the oxidation state increases 3, 4, 5, 6, and then it starts going back down again as you go toward platinum, maximum platinum 4. more typically platinum 2 or platinum 0. Oxidation states for transition metals go up as you go down. So you can get to higher oxidation states as you go from nickel to platinum or iron to osmium. Coordination numbers go, wow, I have very creative spellings, go up as you go right to left in the periodic table. Scandium and titanium, they have high coordination numbers. Zirconium, tantalum, 7, 9. 2 coordinate nickel, palladium, platinum, 1 coordinate sometimes. It's a reactive species, but you know, lower coordination number is over on the right-hand side than on the left-hand side. And I think this is sort of similar to 2, but you know, I mean, you've heard it before. Metal ligand bond strength. Goes up as you go down. So let's keep these things in mind and talk about some example compounds. Titanium hexaquo 3+ ion. Has 1 d electron. This compound is said to be a doublet T state. This is the ground state. One unpaired electron is a doublet. And that electron resides or residing in a triply degenerate level. Okay, so titanium hexaquo is said to be a doublet T because it has 1 unpaired spin. That makes it a doublet. And it's triply degenerate because you can put that electron in any different space you wanted. Let's do another one. Another 3+ ion. Vanadium is just 1 to the right from titanium. So we get 1 more electron now. Sigma star EG, non-bonding T2G. And Hund tells you to maximize your spin. Now we have 2 unpaired spins. How many different ways can you write this electron configuration? You move those 2 spins around. The easiest thing to do is to keep track of where the hole is, of missing the one that's empty. There's 3 possibilities for that one that's empty. So this thing is also triply degenerate. Let's go over to chromium. Now it's one to the right again, this time D3. Obeys Hund's rule. So this one's kind of cool. You've got 3 unpaired spins. That's a quartet state. How many different ways can you arrange those 3? There's really only one way. And so that's a quartet A. Let's do manganese. One more to the right. Add another d electron in there. EG, T2G. And one way to write those electrons out is this way. Or you could also really make Hund happy and write it that way. This here is called the low spin state. This is the high spin state. And this is the ground state. Now, how did I know that? You have to measure it, actually. I mean, Hund would tell you it's probably the one on the right, but you need to know, what does it cost to raise that electron from T2G up to EG? That's the delta O spacing, right? So whether or not that electron goes up depends upon how much coulombic repulsion you relieve. You know, the Coulomb effects change. And the exchange energy changes because you go from 2 unpaired spins to 4. So you have to know the magnitudes of that delta O versus the electronic repulsion and the exchange to get the answer right. If delta O is really large, it's not that likely. So you have to need to know the delta O and the pairing energy. To assign high spin or low spin. Okay. The pairing energy for manganese is about 28,000. While the delta O is 21,000. Okay, so you can gain 7,000 wave numbers by unpairing the electrons and promoting one from T2G to EG. That's the difference between that pairing energy. It costs less to promote them than it does to pair them. So 3 situations are generally encountered. One is you have third, get this right, the 3D transition metals. So here, we're talking octahedral. Okay. Pairing energies are kind of typically 15,000, 25,000 wave numbers. And the delta O is typically 8,000 to about 32,000. Okay, so you see both high spin and low spin. Another one is tetrahedral. Are almost always high spin. And the reason for that is that the T2 and E spacing, which is called delta TD, is about delta O divided by 2. So the spacing in tetrahedral, this is T2 over E now. Remember, it's not T2G and EG the other way around. It's T2 over E. That delta TD spacing is about half delta O. And when the spacing is smaller like that, promoting electrons becomes easier. And that means that tetrahedral compounds are much more likely to be paramagnetic high spin molecules than octahedral ones. I like to say that the smaller delta TD is because overlap is poor. The ligands and the orbitals don't really point at each other very well in tetrahedral complexes. And so the overlap is weaker, and that makes the delta TD smaller. So 4D and 5D transition metals in octahedral have pairing energies that are smaller than 3D metals. It's easier to pair electrons in 4D and 5D metals. And this has to do with the fact that their electrons are more diffuse. And that means that they are more weakly interacting. The electron-electron interactions in 4D and 5D metals are smaller, and that means it's not so bad to pair them. Okay. Okay. The other thing here is that spin orbit effects are more important. In heavier elements. They're larger, spin orbit coupling is larger, and so you're less likely to end up with a high spin kind of a state. And delta O is larger in 4D and 5D transition metals because Bonding is better. Bonding is better there. So they're usually low spin. If you're looking for a paramagnetic transition metal complex, you really want to go with a 3D metal, not a 4D or a 5D. All right, so I'm going to stop there. It's a good place to stop. And that essentially ends the content for the exam. Okay, so I would say exam, covers everything up to this point. And some of the stuff that we'll do in lecture on Monday might be relevant, but it's not the main thing. And I'm not gonna worry about high spin and low spin, for example. But some of these ideas might be useful. Certainly like doing pi effects on an MO diagram might appear. Okay, so I think we're over time now and it's time for me to quit. But as always, I'm happy to hang out and answer any questions that anybody has. And if not, you have spring break next week. I'll be watching my inbox if anybody wants to get together. I'm happy to walk you guys through some of the material if you're struggling. I'd appreciate you reaching out to Ding also and first, but I'm happy to be here for you if you would like it. And I guess that's it. So we'll see you next time.
Thank you.